So let's continue. Next step is, now we have been talking about collecting and preparing data. It's not always that it's possible to collect sufficient data, and that's where you come in with the topic augmentation. And that is a way to produce data based on the data you already have. You can say that, well, just copying the same image doesn't make much help, and that's true. But what we do is to, oops, let's see if it, so we have a lot of operations. We can shift the image content. Maybe if you do some kind of training, it's sensitive just to where it is in the image. If you have well-centered data, it thinks you should always be in the middle. Otherwise, it's not good. Then you can work with zooming, so rescaling, can rotate the images, can also play with the intensity, doing different kinds of normalization, possibly also play with the colors, so do some kind of color changes, doing shearing, so like twisting the image around a little bit. On top of that, you can also add kind of measurement related effects like noise, so using different signal to noise ratio. And you can also add blurring for the optical transfer function to say that you are out of focus or not as focused as you could be or something like that. And that gives you many degrees of freedom to increase your data set using the same information you already had. Here are some examples. These are the blood vessels I talked about before, the retina scan. And here you can see what it looks like. So here we have first the original image, and then we do some kind of elastic change. So every grid point is moving around a little bit. We do some rotation and also do some zooming. And when you do it on the original data, on the grayscale image, then you also have to do the same operation on the mask, which is the label image. And this was prepared for the training of the root segmentation problem. The beamer is unstable today. I hope it keeps with us for the rest of the lecture. No. Let's hope it comes. I don't know what it is. I try and use. And sharing again. Does it come? Yeah, there it is. Let's hope it works better. So that was it. So these are some examples of augmentation that you can do on the images. And the limitations is, first of all, you have to set boundaries on which kind of modifications can you do to still make it look like what it was. I mean, you can always do some more morphing into from one shape to another one, and then it's not really realistic anymore. So this is really annoying. Let's see. I'll try a different cable then. Let's hope that one works better. So let's hope it works. The other thing is that images maybe can't get flipped. It's possible that the patient is a little bit rotated, but upside down is not realistic. And that would misinterpret the information. So that kind of limitations you have to set. And of course, how much you can distort it. Can you recognize it, or is it just noise more or less, or something like that? For this, there is in a Python package called Keras, an image data generator. This is just the head of the health page from that one. And you can see that you can do a lot of modifications. For example, you can have centering for features. You can have normalization. You can do width shift, and then you can say in which range you can do it. You can set a rotation range. Yeah, and vertical flipping, allowed, not allowed, so on. So you can do a lot of different modifications on your data. And this probably requires you to play a little bit with it, but it's a helpful tool, because otherwise you would have to write all these transformations yourself, which is doable, but it would take you probably some time to do it. So it's pretty convenient to have this tool. Here we can set up one example where we have one. We say that we don't want to center, we don't want in different ways, we don't want some whitening. The rotation range should be allowed to rotate 30 degrees. A width change in 25%, height change also 25%, shear also in 25%, zoom even a little bit more, and the fill mode is how to do the sampling. And then here also flipping horizontally and vertically are not allowed. So by executing this, we don't see much. We just confirm that it's initialized. And then we can look at what it looks like on the NIST images. This is quite a lot of code, but most of it, what is relevant is actually this line here. First you load the data, and then you have this line here where it says fit. So it takes the image data into the model. And then afterwards, you call this next function, and this next function is actually producing the augmentation of the data set line-wise. So and then it shows the result. And if I execute this one, you can see, oh, you can't see. See if I can move it up now. It doesn't want to move. Yeah, in this mode, it doesn't want to. Okay, but hopefully, or on your own screen, you can see that there are a couple of rows showing different augmentations. You see a little bit indication down here that the numbers are actually a bit modified. Yeah, maybe I can show it like this instead. So there we have them. So here you can see that they are moving around. It's the same object, but it has been rotated or reshaped in some way. A very large data set is the CFAR 10 data set. It has a lot of images. Here we can see different categories again, airplanes, automobiles, birds, and so on. And from that one, we can do, again, some augmentation. We do some loading. So first, let's load this one. And again, we allow reflecting this time. And let's see what we can get. Again, this running. So here I can demonstrate how the run of that works. Takes a little time, and then you can see here what kind of augmentations are produced. In some cases, it makes sense. In other cases, it looks pretty weird. And that's an indication that this kind of augmentation is not good. So we need to maybe limit the boundaries. So for example, the car here gets just stripes. Here's a lot of stripiness in this, and it doesn't really look like what it should be. So when you do augmentation, you have to also do some visual check that it actually makes sense what we have created. Now let's leave the data and go to algorithms instead. And now I'm going to talk about baselines. And a baseline is a very simple algorithm that is easy to understand, it's easy to implement, and it illustrates the problem itself. And you can see it as a worst case scenario. If you get worse than the baseline, then you're not really good. So the question is, why is it important? So let's start with very simple baseline. You have a model that is more than 99% correct in predicting breast cancer. And the algorithm is very simple. It's just, do I have breast cancer? And you add the information, age, weight, and race. And the algorithm says no. And that's actually pretty good, because breast cancer is apparently 89 women out of 100,000 have breast cancer. So that is 0.09% of the population. So by using this algorithm, we are actually 99.91% correct. Fantastic algorithm, isn't it? But it doesn't actually help those who have the problem. So what we have in a package called scikit-learn, there is a dummy classifier which we import. And by running it, we have this classifier that's saying strategy most frequent. So it's more or less counting how many, which is the most popular class, and that is the one that always gets right. So here we have an example. We have the classes 1, 2, 3, or the IDs 1, 2, 3, and we have healthy cancer. And using this strategy most frequent, and let's see what happens then when we run this classifier. And I'm running it, and we can say that if we enter the value, so this value is some kind of indicator, it's just a dummy example now. Prediction for 0, healthy, great. That is what we expect. Also for 1 is healthy. For value 3, it also says it's healthy. But in reality, it should be that it has cancer. And if we set the value for 100, it's also healthy. So the reason is now we have the majority is healthy. So that is what our model tells us. Looking at the numbers in MNIST, we can do the same thing. We have here a distribution of numbers. You can see the first panel here is the histogram, how many of each image we have. And here are some examples. And we can see that we have 5 ones and as little as 1 out of 7 and 8, I think it is. And then we can see what this classifier is doing. So let's train the model with most frequent again and run the test on it. And oops, so the test says, of course, if you show an image of a number, it's a 1 because that's the most frequent. So most frequent is maybe not the best, but at least it gives you some idea about how the data behaves. And let's test on the images again. Let's see what they do. And looking at the predictions, you can see that we can see that it's a 5, but it predicted 1, and then it goes on until you come to the 1, where it actually hits the right value, and then it goes on finding some more true ones, and the rest is just mispredictions. Let's look at it. We have the frequency of the numbers again, and then we can see actually that we have the majority of 1, and that is why we have this value as output from all predictions. Another baseline would be nearest neighbor. It's a machine learning algorithm that I'm actually going to talk about in some weeks a bit more. But the basic principle of this algorithm is a nonlinear classifier, is that you provide a lot of training data. And when you come with a new value and want to predict it, it looks into in the neighborhood. Let's say you got a point here. The closest is this one, and it belongs to class red. And if you would have a dot here, it would belong to class blue. And that's a very simple algorithm. Sometimes you can also talk about several nearest neighbors, but in this case, we just talk about a single one. In this case, you have 9 neighbors, and then you see that there is a completely different decision line, and also how it behaves. There are more points, so it's not the same data. So let's load the NIST data again and try it using the nearest neighbor algorithm. So, and then we go on. And train this k nearest neighbors. So now we have from scikit-learn, we have imported k neighbors classifier. We initialize it saying we have a single neighbor. We have to do some data preparation, reshaping it, because nearest neighbor doesn't want to work with images. It just want to work with long arrays. So we have reshaped the image. And then we run it, it's finished, and then we go on and look at the predictions. And then we can see here that we get an array. Now we get a lot of different numbers. The question is, how good are our predictions? And it actually, yeah, no, that one was lost. Yeah. The reason why we got, and that should say that it's actually the exact numbers that we took. So let's see here. Now we have tried it, and fantastic. We do the right thing all the time. Great algorithm, isn't it? Now, what we did, we used the same information to test the algorithm as we trained it with. And that's one of the basic crimes in machine learning, that you use the same data for training and testing. So what happens if we take different data? Now we can see that instead here it it should be a 2, but it predicted 3. Here it should have predicted a 4, but it predicted 1. And now you can see that sometimes it does right, at least sometimes, and sometimes it does wrong. So it looks like here that we are around 50%. And with that, we can start looking at how to measure how good we are. And for that, we use something called a confusion matrix. And the confusion matrix contains, oops, hey, where is my pointer? Here it is, yeah, okay. So you have actual true and actual false, and that you plot against predicted true and predicted false. And from that, you can see how good you are. This is just a toy example, so it's not related to the numbers. So let's look at the confusion matrix for the MNIST data. And this we need to run. And you can see, oh, I need to move it up. So here you can see at the diagonal, you can see that it's pretty good at predicting, and around it's doing misclassifications, but mainly in the middle. And then there are some numbers which are also prone to do misclassifications. For example, the 4 has equally many 9s that it finds. And also, let's see, there was another one which also does bad, is 7 to 9 is also doing not so convincingly. But this gives you an idea how good your classifier is. And it's a good tool to check how good your work is. And this would be now what the baseline is showing. And hopefully when you have a better algorithm, you should have all numbers along the diagonal through, because that would be that you actually predict everything correct. Could also be that the data itself is maybe a bit ambiguous, but the algorithm, when it's trained correctly, it should be able to cope with it. And well, this was a short piece. The exercises today, they will be about creating augmented data. And then you also will try to implement the baseline and see how well it works. So today we talked about importance of good data, ideally your own, but if you don't have it, there is a lot of databases out there to help you. And if that's not sufficient, then you can also work with augmentation and try and see if you can modify the data slightly in, say, physically realistic boundaries. And to test how your algorithms are working, then you also, it's good to use baseline algorithms to have something to compare with, how well it actually works. And one way of measuring it is to check in the confusion matrix, testing true positives against false positives and true negatives against false negatives. Next week, I'm going to talk about noise and filters. So then we're actually going towards working with own data in a sense, seeing which kind of features you have in images and how you can prepare them for further analysis. Yeah, that was a little bit short today, but I will be around here till noon for the exercises. And I realized this morning that I forgot to push my latest changes. So to get the exercises, please do a pull on the GitHub or download the new zip if you choose that way. Stefano and we also created a new environment file, and we tested on 4 different computers, and it should work. So I hope you can now get it working. And it was also a different operating system, different CPU architectures. It worked on 4 computers. So I hope it works for you now.